want to talk to you a little bit about the cross product today. So let's say that I have a ratchet and I'm trying to get a bolt off and I'm pushing. So I have a force that's acting upon this lever here and I'm trying to get the bolt free. So I'm just pushing and pushing and pushing. Well, the idea here is we want to figure out how to model this system. So if I have an arm and I have a force and I push it, well, this is like a force acting along this lever. And what we really want to see is we want to see the bolt come up. We want to see it become, unbolted or unscrewed or unthreaded or whatever you want to say. So the idea is if we have a force and it acts upon a lever, you have some resulting vector. Now what I want you to notice is that when I do that, I'm pushing along this axis and this axis is my lever and my resulting force comes out. So if I think about it this way with this sort of makeshift coordinate system, I have a force going along the lever and it shoots up. So this follows what we call the right-hand rule, which is a vector acting along another vector produces a third vector that's orthogonal. And so the idea is if we know that there's some sort of system that causes that. How do we figure out what that resulting force is? So you might remember from dealing in some of your physical science classes that if you had a longer lever, that you're going to get more torque. Shorter lever, it's harder to get torque. So we want to know what the relationship is from R to that lever to that force. Obviously, more force gets you more torque, but what are the relationships of these three vectors? Well, if you come over to this thing, the way we find that is in something called the cross product. So if I have two vectors, u and v, and they have their components here, u1, u2, u3, and so on, then if I want to get this cross product, which we call u cross v, and I want to take a moment to differentiate the fact that we've dealt with u dot v and we've dealt with u cross v, and both of them use an operator that we associate with multiplication for scalars, dot or the x. But they mean very different things when we're talking about vectors. The dot product produces a scalar. The cross product, notice that produces a vector. And you have these components, u2, v3, and blah, blah, blah. It's a lot to keep up with. We're going to learn a shorthand on how to do that in the upcoming sections. But the thing I want you to notice, really, the key here is that, notice that the first component is missing the first component of either two vectors here. So it's the first component, so we do the second, the third, minus the swap. And then we have a minus because we're going to swap the way these things go. And in this one, we're missing the second component. So we have the first and third minus the flip. So again, we're missing the first, we have the second. We're missing the second, we have those. And then over here, we're missing the third, we have those, and then the swap. So you can kind of remember it that way if you want to. We're going to discuss a way that's a little more visual coming up. But I want to point out a couple of things that are very important. A cross product will always be orthogonal to the vectors that generate it. So if you take the dot product of something that's generated by a cross product, it's always zero. It's always the zero vector. It's always zero. Versus if something is crossed with itself, it's always the zero vector. And that one kind of makes sense, right? Because if u and v are the same here, that's going to be zero, that's going to be zero, and that's going to be zero. But the idea here is ultimately we're using this cross product to take two vectors and generate a third. So what that tells me is I can almost create a coordinate system anywhere If I have two vectors, I can generate a third. Now I have a 3D coordinate system. That's the introduction to the cross product.